is the blue screen. The one that connects to the camera, that DVI looking one.
Okay, well, thanks for coming and expressing interest to what we are doing. So, please consider to open MATLAB on your laptops if you brought them with you or on local screens here.
Right, thanks.
And, we will come through subjects that we didn't cover last time, and they are included in your presentations. And if someone has additional questions on the subjects of your presentation, then there will be answers on those. So, what are the what are the subjects that we have to cover? Would it be fair to say that we covered everything we have in the list except the barrier and harmonic potential? Does it sound right, or it could be a little off from the plan? So I definitely remember we were doing number 8, real and imaginary parts of the wave packet, right? And please give me secret signs if you want me to repeat something. So we'll try to squeeze things, but to my memory, last thing that we did here, we were running the code for absence of any potential for free space, and then looking at the wave packet. We'll be mostly interested in this. Yeah. Right? Yeah, here. In plotting real and imaginary part of the wave packet and analyzing that when we set up initial momentum high enough, then it has more fringes. If we put it to 0 initial momentum, it has no fringes in the center and maybe some little fringes on the edges. And what is also we have observed that floating wave function itself is really crazy. One needs to put real and imaginary part, or absolute value square, or like real part square plus imaginary part square. Otherwise, one gets something crazy. Let's run the code quickly and just see that we have it. Please give me secret signs if anyone opposes this plan. No? Okay. So you all have the code, right? To my understanding, the classroom deletes, wipes off the memory. So you need to put it from your email. So look for the email a week ago. The things that I've sent right now are for next steps. Huh?
You sent it on the 18th?
Today is 26?
25th.
25 minus 7. If you're sure that this 18th looks for emails from 18th.
So what the name for the code was WP free AVP, and I'm going to erase everything I created here as a little experiment. So it is the things that you typically observe when you run the code. You see the initial wave packet, then you hit enter, it starts moving, and then some panels pop up. So what I'm going to do is to open new figure and plot so it is what happens if you try to plot wave function without any preparation. So it doesn't look like expected Gaussian sombrero. Why? Because there are real and imaginary parts, right? So instead one should plot real and imaginary. So you do see that they show a little bit fringes, and their frequency increase as we go apart from the center. This one was selected with 0 momentum. As far as you go to the code, look for initial conditions and change initial momentum, then save it. So how do I save things if I, oh, okay, there is a symbol. And then I am running the code once again. So now it does has momentum, so it moves. And if after this exercise I am trying to repeat the line that plots both imaginary and real part of wave function, it is most typical thing that one is expected to see. So because it is just by nature, wave function has real and imaginary part, and from very long time ago we have an idea that of Bohr atom, of oscillating things as a wave. So if the momentum is higher, it oscillates with more denser fringes, both real and imaginary part. And the Gaussian sombrero will come up if one takes absolute value squared. Make sense? Okay. Next thing in the list. Operators in position and momentum space. Expectation values of position and momentum. So expectation values of position and momentum is really easy. Have you been here last? Did you watch the recordings?
Yeah.
Okay. Well, I'll quickly come. And operators and position and momentum space is a little bit more complicated. So you should realize it and understand that you cannot squeeze everything in 3 minutes. So the expectation values a priority. This is kind of super extra. It will not be a surprise to tell that we define wave function in grid space, position x1, x2, x3, as a vector as a vector column. And in the space, operators are matrices, right? So what we did, the main thing, and I hope that Megan hopefully will cover it. So it is first thing in our modeling, and is most important, how to represent momentum operator in this grid space. The idea comes from definition of momentum, derivative. So we need to write derivative in form of a matrix. Please give me sign if you remember this discussion on this blackboard about 2 weeks ago. Give me signs if we need to briefly cover it once again. Okay. Oh, this board is probably better. Are the symbols large enough to see? Mark, can you see from last row? Okay. Are there any objections to the definition? So you select 2 points and subtract value of function at one point, another one, and divide by increment. Slope. Function a little bit further away, a little bit backwards, right? Now, if we do have list of values of, so right now, f of point x1, phi of point x0, phi of x plus delta x, phi of x minus delta x. And this is very long matrix. I'm just a very long vector, and I'm taking just a middle of it. Okay? Please protest if you disagree. No, I'm sure I am here to serve you. If you do not like it, you need to protest. So, how do we implement this algorithm? So if we do set up a matrix that will, suppose we need to know the derivative, so this will be phi prime, and we need to know the value of the derivative at point x. So we do want, I put 1/2 delta x here. We do want to have here phi of x plus delta x minus phi of x minus delta x. So in order to populate this element, we need to select right values in this row of matrix, because when multiplying it will be row by column. The element that will stay in the middle here will be coefficient in front of phi. the element that will stay here will be coefficient in front of phi x minus delta x. The element here will be element in front of phi plus delta x. So phi of x plus delta x should come with coefficient plus 1, and here we will put this over delta x. And here it will come with coefficient minus 1, and here 0, right? Protest if you do not like it. So from this on, we decide that on the main diagonal it will be zeros. On the upper subdiagonal, if we grow this matrix larger, it will be plus 1, plus 1, plus 1, and on this lower subdiagonal will be minus 1. So a matrix that has zeros on main diagonal, 1, 1, 1, 1, 1 here, minus 1, minus 1, minus 1, minus 1 there, and the rest of elements will be 0. It will be matrix representation of the derivative operator. And if you do want it to be momentum, we just put minus I h bar. And to keep this delta x, we just write delta x until it is P operator in matrix representation defined in coordinate space. Because we are taking points at the coordinate space, right? Alternatively, one can define everything in momentum space, which is crazy. If you do not feel comfortable, you better skip it to avoid confusion, and maybe return it to on the next iteration. Any questions about momentum operator? Okay. What next? What is next? Well, we covered it because otherwise it has no sense to go further. Operators in position and momentum space. So now this is momentum operator defined in position space. If we define momentum operator in momentum space, it's much safer than to use this joystick. So P in momentum space. It will be just P1, P2, P3, P4. So values of momentum, or we can set up it as P. Nothing was wrong here. We'll redefine it once again in space. So we can put central value P0 like momentum 0, delta P, 2 delta P, minus delta P, minus 2 delta P, and zeros everywhere else. So momentum operator in momentum space feels itself very comfortable. It is just simplest possible operator. Same as position operator in position space will be just diagonal. So based on these two things, one can redefine everything. One can set up the Hamiltonian operator and evolution operator, and then plot everything in the right space. Since we are normal people, not too much in the strange spaces, we prefer to intuitively analyze whatever has been plotted in the coordinate space. Therefore, most of time we analyze wave function that plotted as function of time and position. Although the code does some calculations in momentum space directly. So there are three methods. Second and third are in position space, and number one is in momentum space. It is very, very close to your homework number 2, if you still remember, most likely not, when we were finding expansion coefficients of the Gaussian wave packet along plane waves and then returning back into coordinate space. So momentum space is basically expansion space of expansion coefficients along plane waves. So for you to stay awake and not too much stressed, just try to fall asleep and think about more pleasant if I'm not talking about your favorite subject. Otherwise, it will be too much information. So do not concentrate on things that you are not presenting. Otherwise, it will be hard. So if you are listening to me, it's your responsibility. So I'm very briefly cover this. It's not yet sufficient to write the code from scratch, but it gives basic idea. There are, if you inspect through the code, if you have time to do it, which may not be the case, you'll see that Hamiltonian and evolution operator are defined 3 times. First time for momentum space, and then 2 times in coordinate space. So I'm making a little. Oh, it doesn't allow me marks. It's already graphics. I'm making a little symbol here to return, and instead of continuing here, let me quickly jump to commutation of operators. So it's a specific subject for Andrew. This is connected to what we discussed right now, and this is most theoretic and complicated subject. Sorry to give it to you, but you were not at the time when people were voting. So what I'm going to do, the operators in this code are matrices. And we do know from linear algebra the rules of matrix multiplications. So if we multiply 2 operators, it means we multiply 2 matrices that correspond to them. And then one can pose a question, what if we swap the order? So one can try the rules of quantum commutation that we learned theoretically in this practical implementation. Set up like position operator, momentum operator, multiply them in one order, in another order, and then plot what comes up. It is expected that by commutation of position and momentum, one must get imaginary unit times Planck constant. But we may check. Maybe it all was lie, and the code tells the truth. Or this all was truth and the code is lying. Or we have some, if they are in a reasonable inconsistency, we have some agreement, some idea explaining what is going on. So to practice commutation of operators, you do not need to run dynamics. You need only top part of the code that defines operators, and then you plot with them. What else we need to know for this subject? We need to know what Beth presented on previous presentation, how to visualize a matrix. Because operator is a matrix. After commutation, we may want to visualize it. Okay. So if you forget what is the size of your matrix, you just type size. So right now I'm screening through the code and searching for definition of momentum operator in position space. So this P operator is momentum operator in momentum space. And this Ham, which is not food, it is Hamiltonian, it is defined in momentum space. So for most, it's only theoretical use for most of our investigations. It will be not helpful. If you do have, close your ears, don't listen, it is excessive information. If you need to transform wave function from position to momentum, you apply Fourier transform once. If you want to transfer operator from position to momentum space, you apply Fourier transform twice in direct and conjugated way from left and right. You haven't heard it, it's too much. Okay, so second Ham is Hamiltonian operator where P, momentum operator, is defined in the X space. So we are going to explore two things, the X operator and Px. They are, as you see, they are of the same size, right? So both square matrices 200 by 200, which means we are allowed to multiply them. So I may open a figure, if I'm not sure if it is opened before. And before starting, I may do bar 3 of hop, which is not a hip hop, it is X operator. And if I rotate it, you see it is 0 everywhere except main diagonal, where it shows from minimal position to larger position, right? Trivial. If I want to visualize Px, it may give an error because we wanted to, because we know that it is imaginary. So this, to big extent, I'm repeating what we briefly discussed here some times ago. So this strange thing, and presenter may show it moving or just show a couple of snapshots. It is a matrix representation of momentum operator, which we talk here. So here we set up it to be 0, 0, and either 1 or -1 along main diagonal. What you see here, it is more complicated structure. The additional values to the left and to the right of the main diagonal are added to be more precise, to reduce the error. So it is higher order corrections to describe derivative infinite differences. The edges are needed to match the boundary condition, to allow wave packet to reappear from right if it disappeared on the left. So that, because we have a finite box, and we should understand that it is like set of equal rooms. If I disappear from this room, I appear in the replica. So we did two operators. Now we may check that size of x times px is the same. It's just a trivial check. Px times x operator is the same, and then hop times px is okay. Now we can call it and plot. So now we have defined commutator, and we may plot it. Which domain does commutator belong, real or imaginary? If x is real, momentum is imaginary, and we multiply them. Yes. So we can try to plot it as is, but you will not enjoy much. So it is much more reasonable to do imaginary. Something doesn't go on my expectations. What I'm doing wrong? I'm trying to plot while one needs to. I wasn't carefully listening to Beth. So there are specific tools to plot three-dimensional things. So by some reason, imaginary part is much closer to 0 than to Planck constant. And it would be not right to say that Planck constant is small, therefore it is here. We are using atomic units, and Planck constant is set up to be 1. So there is something, there is a mystery here that a presenter needs to resolve, and we may communicate by emails. But both our theoretical approaches in class and computational modeling here should be right. So there is an answer what is going on. And if we use the third method, we see it is much closer to our expectations. So this is main diagonal, which on this axis is very close to 1. The edges are due to boundary conditions. So the third way to define momentum operator somewhat matches the expectations. And what one needs to do to analyze it further and tell something reasonable, one may enlarge the region of interest and make sure that see, it is zeros everywhere except the main diagonal, which would correspond to unitary matrix multiplied by Planck constant and imaginary unit. Enough. Try to do the same, make screenshots, and present your best understanding. Returning to this point. Expectation values of position and momentum. In simplified sense, it is main thing that the code is doing by now. So it propagates wave function in time, and at each point of time, it does calculate the expectation value of position and momentum. If it is the one who presents may focus on the, probably will be not time for presenting, but for yourself, look on the lines of codes where these expectation values are defined, and I will do it in a minute. And then look on the visualization of these expectation values as function of time, where we do see confirmation of our theoretical modeling from the class, that if there are no potential, position increments linearly. Right? Momentum is constant, doesn't change in time. Width, uncertainty, it's not your problem, it's problem of the next presenter. We excluded it from here, passing of the wave packet through the walls, through the edges of the periodic boundary conditions, so you may cover it if you have an idea what it is. So I'm going to demonstrate expectation value of position linearly changing, and then going through higher value of momentum, it will show some counterintuitive results, which was already enjoyed by those who were here last time. So I'm going to clear the memory, well, not my memory, but memory of the computer. And although the pictures are nice, I just want to have everything super simple. And now wave packet the operator. So running once again. It moves from left to the right, and the width increases. So if you see, there are some panels where position and momentum pops up, and you see position changes linear with growth, and several lines correspond to several methods. Momentum doesn't change with time, because there is no reason to change the momentum. Where is it encoded in the code? It should be in the place at the end of the loop, after we have moved forward with evolution operator. So this one is expectation value of position. And this one is expectation value of momentum, which is wave function conjugate, operator, wave function not conjugate, right? As we defined in class. And it is what was raising. Now, if we jump back to the very beginning of the code and set up the initial momentum twice as much, or 6 times, or whatever, 3 times as much in atomic units. File save. I'm going to. So if you're presenting, you may want to make screenshots. If you're just doing it for your entertainment, you can just delete the panels. So running once again, initial distribution looks the same, but it is expected to move quicker. Moves quicker, opa, and reappears from the other side, right? Because of periodic boundary conditions. And then if you look on the position as function of time, it grows to maximal value, and then it reappears from 0, right? Any questions on this subject? 1, 2, 3. You will ask questions to the presenter. Next, energy and uncertainty of position and momentum. of free space and harmonic oscillator. I did a crazy thing. I jumped together complicated things. So I move for free space, and then about harmonic oscillator you'll speak differently. So any we're just at the right spot of the code. So this combination, this definition of expectation values works for anything. And you may want to practice it for any observables. Just set up right operator. So we may set up the Hamiltonian in the sandwich of these wave functions, or we may set up operator of standard deviation of either position or momentum. And then we may watch how they develop in time. So if we look for standard deviation of momentum, it is defined here. So the momentum operator minus expectation value of the momentum, right, squared, will be a standard deviation. And then you can plug it into the definition of any expectation value in quantum world, right? So if we are going through the code, running it, maybe with the same initial conditions. One of the panels does display the variation of position, which is also, which needs to be defined very, very close. I think it is variance. X operator minus the average value of position. So if you look on a time limit before things, before the wave packet hit the wall, you'll see that the variance, the uncertainty of position grows quadratically as it is expected from our in-class and homework consideration. You remember it. And last time when Braden was presenting movies, he was showing, based on our class material, how wave packet becomes broader and broader. So this broadening is going on quadratically. But if we did set up our numerical experiment in such way that wave packet passes through the door, at a time when it reaches the edge of the simulation cell and reappears from the other side, it is mostly delocalized. And the width defined formally will be incredibly high. So if we change so if you look at the interval of time when this thing is happening, the uncertainty will reach values of the size of the simulation cell squared, right? So there is no big science in this. It is just a sign that we need to select conditions of the simulation in such a way that we avoid unphysical situations. Energy and uncertainty of position and momentum. So position yes, momentum no. The uncertainty of momentum is accumulated in the variable AV average SP. So I may just make a figure, the plot of this. So it has this strange form because any variable may have real and imaginary part. But we should understand that imaginary part, which is typically y-axis, is 10 to minus 13, which means it is 0. And for the real part, you see that the values on the axis are not changing. So the uncertainty of momentum is constant. It doesn't grow, doesn't decrease for the free particle. This is sufficient to prove it. But if you want to provide to audience more convincing argument, you can plot only real part and show that it has some numerical error, but it is within less than, substantially less than 1%, right? So uncertainty of position, uncertainty of momentum done, energy. Let's see if it has been defined anywhere. If not, we can just type it ourselves in the same So as an operator inside, we can plug in the Hamiltonian that has been already defined. And right now, I'm not doing the accumulation over time steps. It's only the value of expectation value of total energy at the last step of time propagation. But if one will take the computed along the trajectory, it is expected to be the same, because for free particle there is no reason for energy to change. And actually for any model in this course, the total energy is not going to change. It is going to be conserved, right? Because we do not model mechanisms for energy dissipation or leaking out of the computer or out of the model. Because of conservation of energy, it is expected to stay the same. If you do not know what to do, it is you can always, well, it is not the definition of undergraduate life, but if you have free time and curiosity, sometimes methods 2 and 3 give different answers. And if we set up increment of space, if grid points are close enough and time increment is small enough, then they expect to converge. But right now, to make it least expensive numerically, we do use substantial, relatively large increments in space and time. So they differ by whatever 40%, which is not super good. Numerical value for our momentum equals 6. 6 squared will be 36. Divided by 2 will be 18. So this one is more expected. P squared over 2m, where Planck constant and mass are equal 1 in the atomic system of units. Uncertainty of position, energy, uncertainty of position and momentum for free space. Make sense? Harmonic oscillator, I'm going to postpone it. Let's jump to whoever volunteered to present barrier. Good choice. Did I miss the finite size box? It was in the original, but it is missed here. Strapping in the box and the barrier here. Okay. Oh, you will sit nearby. So box and barrier. Right? What are they? Why do we need them? If we need to finish the course in 1 week, and we still want to have minimalistic connection to real life, I'm going to point on here and draw something. So if you do want to have minimalistic connection to real life, we may plan on describing molecules and materials that may undergo either dissociation or ionization, whether we talk about dissociation of ion or ionization like electron leaving the system. If we do have infinite box, then whatever we model with, the particle is confined there forever. But you know from your general experience, molecules can be ionized. You can remove electron from there, right? Or if it is, if you speak on, let's talk about it, which means electron physically goes away from the sweet spot where it has been attracted to. So this is possible if the barrier is not infinitely high. If there is a finite width of a barrier and we communicate it enough energy, so the wave packet has enough energy to go away. Right? What is photo effect?
Photoelectric effect.
Yes.
When you shine light on something, electrons basically leave.
Everyone is with us? So what is the main principle of photoelectric effect? Main qualitative characteristic? Does any wavelength allow for electron to leave the system?
No.
So can you summarize me in verbal form? Not any. Is it like 600 nanometers width, 700 nanometers not width, 900 nanometers width again, or it is something simpler?
Depends on the material, doesn't it?
For fixed material.
It's just a threshold where if the frequency is high enough, then it should just be able to kick out the electrons.
Everyone is with this explanation? So photoelectric effect doesn't insult anyone. Okay. So if the energy of photon is higher than the threshold, so if it promotes electron higher than the depth of the barrier, then electron may leave. So it is one. In German, it would be Gedanken experiment in our heads. But we can do, and then a barrier can model some realistic systems with photoelectric effect. Another situation, trapping of an electron. If you have an electron that moves, and suddenly it got trapped, which will be opposite to ionization, is called affinity. Tell me it in chemical language. You all are much better chemists than I am. With removing electron is oxidation. Contributing electron is reduction. So as soon as you make finite size of the barrier, you become able to describe redox reactions. Of course, in very ugly way, because there are no atoms with square walls. But in principle, you can do it. Enough as a motivation. Now, so this was the finite width box. Barrier. What if you flip this image upside down? 0, 0, 0, non-zero, 0 again. What does this model for you as for chemists, for us as a chemist, for chemists in the whole civilization? Here, the X was position of electron. Here, you can start thinking of X as position of, let's say, proton, or reaction coordinate of something more complicated. So we can say this is reactant, this is product, and this is activation energy. And then we set up an experiment where initial momentum, initial energy depends on temperature, and then we tell if temperature is high enough, it will be thermally activated reaction. If not, it will just repel back, no reaction. Right? So even with these two models, you can hug the whole manifold of mostly all reactions. We would do this if you would finish the course in a week. But we will have time to become a little bit more precise. But now it is enough as a motivation. How do we define finite box and barrier? Yes. So the height and width, right? Height and width for both of them. So we just need to program it. We need to program it you may have realized it, or if not, listen to me now. Now, if you were relaxing and protecting your brain from too much of exhaust, now it's time to wake up. It is something very simple, very practical, and very helpful for the rest of the course. It's only one line to change to convert our free space into either barrier or box. So I basically uncommented right line and renamed the code wave packet barrier so that I have both of them in the directory. And the steps to describe barrier are already included. So in my version of the code, it is lines 25 and 26. And 27, okay. As always, I was lying, it is 3 lines instead of 1. But in principle, it's still very, very short. So I'm going to erase the stuff here on the board and give a little introduction how these barriers are encoded. So if we do have grid points with delta x between each of them, x1, x2, untitled, x sub n, right? Right now at current parameters it is 200, but you can make them 1000 or 100, whatever you want. So, and we need to define potential, which will be stored in a variable v. So we need to know v of x1, v of x2, v of x sub n, right? And we do want that these values will be 0, 0, last one also 0, but in specific range in between, it will be equal some other potential, constant, v naught, which we can define separately. So we need to define where to start populating this matrix with new value and where to stop. So there are 2 parameters, width, where to start, where to stop, and heights, which will be v sub 0. I think it is done. Well, we need to throw one glance more. But it is already here. So there is a variable that hasn't been used yet. But you know that there is a command zeros that populates matrices. So 1 means the matrix will be a vector. One dimension will have only 1 element, and another dimension will have so many elements. So this x2 minus ab will be number of grid points before we start non-zero values. Then ones means populate matrix with number 1. Zeros populate with zeros, 1 populate with ones. Again, vector of the length 2 times AB. So AB will be from the center to the edge. AB. And then we repeat again. The rest of the vector is populated with zeros. So zeros, ones, or whatever, 0.5, zeros. So it will be vector populated with either 1 or 0. And then we multiply everything by a constant at the front. And if you scroll to the place where HAM, H-A-M-2, is defined, which is not food, but Hamiltonian, you will see that it is defined as kinetic energy plus this symbol V. So whatever we populate in the symbol V will be immediately in the Hamiltonian. So as if you look in the code, you will see that at the very beginning, the variable V naught is set up to 0. As immediately as you set it up to something different, you will have a barrier. Or if you put it negative, it will be the box, right? So for presenter, difference between barrier and box is just sign of this V naught. What else? If this parameter of width is small enough, then quantum tunneling is possible. So the activated reactions may depend on the not only on absolute height of the barrier, but also on the size of this forbidden area in the reaction coordinate space. Or if you are talking more about electrons in semiconductors, the tunneling depends on the thickness of insulating layer. So this right now we will not modify it, but later on a lot of things may change if you keep the activation energy the same, but the width of the barrier is changed. And for box, you already know that the size matters. It may change a lot. So both for box and barrier, it changes a lot. Where do we set up this V naught? You are free to set it up anywhere you like. And just for comfort of initial consideration, I did place it as a fraction of initial energy. So if you are talking about a barrier, then 0.5 means that it will be always sub-barrier. It will have not enough energy to overcome it. It is made so that one can reproduce same qualitatively the same results for different values of momentum. But you can play with bare numbers and put V naught equals so much in atomic units. How much kilocalories per mole is in 1 electron volt? I hate this question. I will try to avoid it in the rest of the course, but just mark it on the margins of your notebooks if you do them. If you do not do notebooks, just save it somewhere on the background of your memory. So electron volt is a good unit. And it is a little bigger than standard chemical unit of energy, kilocalories per mole. And so the yellow light is about 2 electron volts. Temperature is about electron volt divided by 40. Thermal KT, thermal energy at room temperature, is about 1/40 of an electron volt. But in atomic units that we use here, 1 equals 27 electron volts. It doesn't mean that we all need to put energy equals 1. It just gives you a range. We use them here because if one goes into the system of units, then one doesn't need to take care of numerical values of mass of electron and Planck constant. In this system of units, they equal 1. You may stop listening now. I've told main thing. The rest will be technical details. Maybe not very challenging, but boring. So you may not wait for me and just set up. Originally it was 0, and here I put it 0.5. But you can put 1 or 2 factor and try to run the code. Or you can put minus 0.5 and just see what happens. if you plan to save your work as an image, as a movie, you may change the name and then send it as an email to yourself in case you do not have access to MATLAB at home. Because movie is always better than any explanations and even better than figures. You just show the movie for 5 seconds and then you can tell, I'm done, here it is. Clearing everything, erasing. Erasing. So same initial shape. Now it gives you, so right now well, for systematic analysis of parameters, there will be sufficient space and maybe it will be assignment for one of the MATLAB homeworks. But now you may look on the in principle things that you may observe. So for a barrier, if the energy of barrier is high enough, or if the height of the potential is low enough, then the barrier will come through, right? Since it is quantum particle, not classical, it may come through not 100%. It may split, right? In oversimplified way, chemical reactions can have yield less than 100%. Right? So what if I change the value of V0 to 1.5, where E0 is kinetic energy of system. So right now I'm intentionally setting up the energy of barrier higher than energy of the quantum particle. So saving, erasing. If I would be presenting, I would make a screenshot of this image. I even can make it once. But if I'm not presenting, I'm just erasing them. Otherwise, they will populate the whole screen. So running once again with expectation that now barrier is higher than kinetic energy. What are we going to see? Passing or reflecting? Huh? Both. If we are in the middle, if we are very far in one or another regime, we can see 100% reflection or 100% So London was correct. It is both. It's like 50% yield reaction, right? So part came through, part reflected. If, is it Christian or Beth?
This current one?
Yeah, Bear.
Beth.
You are doing Bear.
Oh,
Box? Okay.
Berry. Okay.
So you may try this experiment and make screenshots, both of you, and then you decide what you present. So, and if we increase this ratio to like 10.5, what should we see then? Reflection or passing through? If the height of a barrier is 10 times higher than kinetic energy. Huh? Reflect? Bounce back. Right? And then, if you have time, you may also analyze our observables. Like position, it grows in positive direction, and then after reflection, it starts going to negative direction, right? If I bump by my forehead into the wall and reflect, my velocity changed to the opposite one. And here it is exactly the momentum velocity. It was, whatever, +2, then it was a transition period, and then it became -2, right? Because it reflected. While if it would be the reaction is close to 100% yield, it will stay positive, but it may change the absolute value, going a little slower, but in the same direction. So 3 minutes is a very short time. So I would probably present a couple of figures like this and move it. Let me see, how do we formulate the questions? Box. Find across cell, okay. Visualize potential and probability distribution. Well, this green stuff is potential,
Okay.
right? So it's how wide it is, how high it is, and you can find in the plotting commands where it is added. Or you can just open new screen and type plot V, capital, and see how the potential. So it's plotting of potential. Or you can do plot x, comma V, comma x, comma prob 2 for potential and probability at the same time, right? More or less done with barrier.
Yeah.
You-
I just need to show the video.
Well, majority of the class is here, but in case someone took my recommendation as a truth and was sleeping, you may be the only one who communicate how quantum passing through the barrier. So summarize as much as you can in 3 minutes.
Okay.
But yes, you're right. Video and couple of observables is the best way.
Okay.
Austin, your subject is postponed again. It is much easier for me to speak about box than oscillator. So I'm going to close, and now minus, which will be a box. So if we set up initial position of the, should be x naught somewhere. So x naught is set outside of the box. So the electron is outside of the box. Box has negative potential. It means we are modeling reduction reaction, right? Electron is getting trapped by a molecule. So maybe the initial velocity was too high, and only a small fraction got trapped. while part passed through, passed reflected. So this analysis is possible only with quantum description. If you have quantum classical particle, it will never reflect back from the deep, right? It's either pass through or get trapped. But here, yes?
Did you change anything besides the initial?
No.
It was just that, like changing it from 0 to 1.5.
Yes, yes. But you are free to try different options, like putting V0 as absolute numbers, like 0.1 or like 0.5, and see how it compares. Just in a hectic, one can imagine some crazy numbers that will blow up everything. Therefore, I'm doing these fractions. So what if we try a little smaller? So right now I kept the same ratio of kinetic energy and the depth of the box, and you see it is less reflected and bigger fraction is got trapped. So slowly moving, less energetic electron is easier to trap. And these fringes would correspond to very high eigenstate of the particle in the box. The higher the state, the larger number of fringes. So the box is here, and right now there is no effort to draw the potential, but the size of potential is the same as for the barrier. So from here to there. So we may also try to model the oxidation or photoelectric effect, to place electron wave packet inside the finite width and see whether it will stay trapped or will leave. So for this setup, we may set the initial position inside the box. So if the box is high enough, nothing leaves. So it did reflect and stayed inside. If we are curious, we can repeat the same numerical experiment with a little longer time of experiment. So I'm increasing n tau to like 4 times. So it looks, to some extent, very similar to our homework, where we saw oscillations of the wave packet inside the box, right? So if the energy of wave packet is smaller than the height of the box and it is initially prepared, it will not go away, it will just bounce from the walls and perform something similar to oscillations. Now we may change the ratio of the kinetic energy and height of the box and see whether it allows for photo effect. So this means that we are exciting above the threshold and it does leave. Right now you have seen the reappearance of the other side because we overused our allowed limits. So if we simulate for long enough, there will be shortcomings of the method, the appearance from other side, which is not truth. So if you take shorter time, it will not reappear from here, and you can trust. But we have illustrated two regimes of photoelectric effect. One smaller frequency that excites electron, but it stays inside the finite depth barrier. And then the excitation energy higher than the depth that allow electron to leave the system. Ionization. So you may play a little bit with these parameters, catch them into videos, and if I would be doing it, I would just call the video different way, and each run I would put like numbers. If I have limited time, I would generate like 5 or 10 videos, and then when I'm not in a hectic, I would just watch which of them is better and put the best one into presentation. Make sense? Any questions? Okay. Feel free to ask after or by email. Transmission probability. This is most appropriate for Christian, or for no one if we all are busy and tired. So I'm remembering about it, and we still have a little time. So what is transmission probability, who needs it, and do we need to invest our intellectual efforts into it? So we already celebrate the strengths of intellectual development of our civilization, because we agreed that even with these initial steps of quantum modeling, we can do thermal activated reactions, we can do photoelectric effect, we can do reduction reactions, trapping of electron. But by now, we do everything on the qualitative way. We are telling reaction goes or reaction doesn't go. But we may want to have it quantitatively, right? So what should I do in the case of this barrier if my finite state looks, let me try to draw something that we have observed in the simulation. I see that it is like about 50% yield, but I want to say exactly. Maybe it is 55 and 45. How do I do it? If this variable is absolute value squared by method 2, so probe 2. How do I define the yield? Or transmission probability. Transmission probability. So if you know initial and final coordinates of our reaction cell, and we know the midpoint, we can tell that part of the probability distribution that is to the right is transmission. So if we take this probability distribution, which is wave function squared, and integrate it from center to final, we can tell that it is transmission probability, right? Or yield of reaction. And 1 minus this will be yield of no reaction, probability that reaction didn't happen, or reflection probability if you don't want to care about actual reactions. So it's reflection probability. Or if you want to be very consistent, we do not believe that this equation holds, we can literally define reflection probability as integral from x initial to x0, say x squared dx, right? So if I would have time, if we would have time, it would be a very reasonable exercise to encode these two lines, accumulate this data at each iteration of the simulation, and then plot them as another observable. So how the percentage of the completed reaction changes with time. Would be really, really helpful. I will leave it for the future, maybe nearest future, but now the main goal is to cover oscillator, which may take time. If you have a few seconds left, I'll do it. If not, you may try doing it yourself, or you can try to do it in class, in the lab next week. But this skill will be needed for our final project, because many of you will select to model actual chemical reactions. Okay? So it was transmission probability. I should probably type here reaction yield to attract more attention to the subject in the chemical audits.
So should I cover that or should Beth cover that? Because right now it's under Beth.
What is the transmission probability if everything is confined? One can use the same, like,
Same thing either way.
same idea there for removal probability, but it is not standard. No, it is more appropriate for you.
Okay.
So you both can skip it, or you may focus on it.
Okay.
Oscillator. Can I erase this stuff? Right?
Yep.
Well, today, the camera, I don't know if it focused. Oh, okay. Now we have it photographed, for sure. So it doesn't want to rotate, but it follows the focusing and zooming in. I hope it is not me who broke it. But it was great fun to operate it. So I'm going to erase it and switch to the oscillator. So the variable v, which is vector defined in all grid points, is what gives us a potential, right? And we do have a variable x that gives variable x that is defines grid points. So we can simply write v as some function of x. And if you want to define the harmonic potential, we need to set up the equilibrium position, which is most naturally to place in the center, but later on, in some research projects, you may set up it away from center. For example, if you have two potentials, like double L potential. And then you may want to define the stiffness, the rigidity, the Hooke's constant, the frequency of the potential. So m omega squared 2x minus x. X naught is already reserved for initial position of wave packet. Let's call it x1. That's it. You just do it and then run wave packet again and again with different momenta and see what happens. And it will be a big illustration of things that we will derive in class in a week or 2 weeks from now. I will do it in a minute. There is an important comment. Anytime we come into class, I'm exhausting your patience by discussing which real systems can be modeled by harmonic oscillator. So until now, we were mostly thinking of electrons in this computational model. But if you are thinking about, if you are describing oscillations, you may want to think of the nuclei, like proton or something heavier. So mass of proton divided by mass of electron. How much are they different? Who is heavier? Yes. How much? Huh? No. A lot is if a stranger catches you on the street or in a store, like I'm a scientist. What is heavier? Is it a lot? Is it like 10 times heavier, or 10 to the 15 times heavier, or Avogadro times heavier?
Yeah, that is like 1,000.
10 to the 3,000, which is the same. Other options? Very, very close. I would narrow down the question. How many thousand times? 9,000 or 2,000 or maybe 5,000? Now I'm justifying that we have a physical chemistry course, finally. What does Wikipedia tell us? Okay, so 2,000 about. 7 or 6? Okay. So if right now we are not going to make these changes, at least I will not do so, because in hectic one can screw many things. But in implementing this formula, one can go to the very top of the code and redefine. Right now, the mass is defined as 1 in atomic units, right? But if you are going to speak about proton instead of electron, we may set it up to this number. Or if it is a carbon, we may multiply by 12. If you want to be really, really realistic. And if you want to set up a frequency, then we should think about something really small. Because in atomic units, 1 is 27 electron volt, which is very high in the UV. So one may divide it by about 30 to get to 1 eV, and about times 10 to get to in the infrared. So omega should be selected of the order of like this number to be in the infrared region. And the x1 for here for initial position, right now for our selection of number of grid points, 200, and delta x, which is 0.4, center point will be 40 atomic units. But again, right now it is for electron. If we go for nuclear motion, the ranges of elongations from equilibrium will be much less. Will be picometers and about like 2 to 10 maximum of atomic units. So let's go to the code. And so I do not have well-prepared values for these parameters. And by putting right or wrong, reasonable or not reasonable values, one can get very far into problems. What I'm going to do, we'll try to make luck of defining maybe X equilibrium will be more reasonable. Save. Aha, it oscillates. But see, right now, nothing is wrong. So if you look on the position and momentum, they both oscillate harmonically. So it was a not too bad guess. And I'm going to erase this line, which was designed for linear motion, the width here. So what is interesting, which scientific questions you may ask yourself, or we may ask ourselves, if we start playing with harmonic oscillator. For example, right now it is a harmonic, which means that independent of the initial elongation and momentum, the frequency of the oscillation should be the same, right? We may double check it. Like right now, for our simulation time, it made 1, 2, 3 periods. What if we double the initial momentum? So the potential is very, very steep, so high that we do not see it on this scale. The question was whether the frequency changes, whether we go from whether number of periods change. No, it doesn't. Amplitude change, it starts moving on larger amplitude, but same number of periods, meaning the frequency does not depend on the initial amplitude. What else? remember extra credit question from last theoretical homework, which was solving coupled system of two differential equations. Those I probably wasn't declaring, but it was simplified without any constants equations for position and momentum expectation values for harmonic oscillator. One acting as a cosine, another as a sine. Right now, our x oscillates along equilibrium as sine because we did set up initial condition to sit at the zero elongation, and we just kick it with non-zero momentum. But they behave with a phase delay. These two conjugated variables oscillate with the same frequency with a phase delay, right? What else can you observe about harmonic oscillator? Which questions can you ask? How does one formulate the uncertainty relation for harmonic oscillator? One expects that product of uncertainty of position and momentum should be no less than Planck constant square with some coefficient. As you saw in many other numerical experiments, this product grows. But here, if you remember the movie oscillation that we just saw, the wave packet is confined by this potential. It doesn't change too much. The uncertainty stays relatively small. So one can look on the uncertainty of position and see that instead of growing, it oscillates, which is like interesting discovery that one can make with this code as an instrument, for analysis. Which other questions can we set up for oscillator? I think it is enough. So please try to play with such values that would allow better visualization, because right now it is not perfect. Axis. So I'm trying to find the line that sets up axis and increase the value on y-axis. This may make it a little better visualized. Axis manual. I don't see it, so I shouldn't hesitate. Axis. So on X it will be from 0 to 80. On Y right now it stays from 0 to 0.12, and we may increase it to like 0.3. Let's see what happens. a little better, but insufficient. Let me stop it and save. Okay, better. So now we see the shape of the harmonic potential, and we see this wave packet that goes from left to the right. When it comes to the turning point, the potential energy increases, and it kind of reflects, but in a softer way, right? So we play something like this and show it as a movie. Right now, we did set up the initial momentum as a kick on 0, but we can set up 0 initial momentum and position away from equilibrium. And if you do set up these elongations big enough, compared to the size of the grid point, you see how numerical errors are accumulating in one method and not accumulating in another one. So it is more experimental work and sharing your experience. I have covered subjects that seem to be relevant to presentations. Energy, uncertainty. Well, energy, same, it will stay constant because we do not have dissipation. Uncertainty, we briefly covered. Harmonic oscillator. Good. Anything you want me to cover right now? Or is enough input? Well, I will sit here and we'll stay ready to answer questions.
This is less for everyone else, but I don't remember how exactly to save and upload videos from MATLAB to like PowerPoint.
Okay, good. Let me do it. On Friday, London will teach everyone, but today it's my turn. So here's the list of files. Right now we are doing harmonic oscillator. Off. Save. So right now the list of files, it has some AVI files, but we need a new one with this name. So let's run once again. So as it goes, there should appear one more file. Oh, it already appeared, but probably it is not yet populated. As we have this thing developing, it goes on, and now it should be ready. So if I have forgotten in which directory I'm working, pwd, which is password detection. Go into PowerPoint. Insert, there should be insert video, right? Video on my PC. Coming to the right. Directory. Clicking. Presenting. Running.
Okay. Sweet.
And you may also practice uploading it to YouTube. So if you logged in with your password, well, it is self-evident, simple, but you better make sure that you can do it. Downloads. And here is the link that you can copy. Here, publish. And now it is available for, well, it will be available in a couple of seconds for the rest of the world. And you can share it with the group. Okay?
Yep, sweet.
Meeting is over. Thank you for being so enthusiastic about this exciting subjects. I'll stay here just in case if more questions are popping up, but I'm confident that you have more than enough input to prepare outstanding presentations.
With the alternate methods of modeling electron dynamics, did you just want me to kind of give a brief overview of each of the methods that your code runs through?
As much as time allows.
Okay.
You may cover propagation in momentum space if you have enough confidence in it. You may try.
I have to brush up on it, and I don't know that I'm going to want to do that tomorrow night. I'm probably going to get some sleep.
You guys are already doing a lot of extra work, and the class progressing above any expectation. So if you want, you're welcome. If you don't, it's not a big damage to our learning process.